summarized here. It's a steel structure. It's the steel structure, and as soon as you see this, you should realize one thing. You cannot model this problem with all solid elements. In other words, do not. It's not that you cannot. You can, but you should not. Okay? Do not create this part like that and then say, okay, mesh it for me. Okay? This is to teach you hybrid analysis. You look at this based on the stuff that we have done in class. You know that this piece at the end must be modeled with solid elements. This sheet, think about this plate, must be done with shell elements, and these must be done with beam elements. Now, these ends are clamped, the ends of the beam are clamped, and this thing sags under its own weight, okay? Now, notice that it says all components are perfectly welded together, okay? In other words, we're assuming that this piece, this solid piece, is somehow bonded, welded, completely fastened to the plate down here, and the same thing with these beams that are connected to that plate, okay? There's going to be substantial deduction of mark if this problem was given to you, and it was a previous test problem, and you did it all with solid elements, okay? Now, it says use all planes of symmetry, and although it doesn't say here, but oh yeah, use all planes of symmetry and the most appropriate element. We already talked about the most appropriate element. This must be done with solid, this must be done with shell, and these two with beams. Now, as far as the plane of symmetry is concerned, you look at this problem, just stare at it for a couple of minutes, think about it, use your imagination. This is symmetric along that line. In other words, I don't have to model the whole thing. All I need to do is to model half of it. Of course, remember, you have restraints that are going to be imposed later on because of the symmetry. And also, when you do half of this, you don't have to do this other beam, okay? So you just use the one in the front or the one in the back, either way. Now, the other thing is that the problems that I've done in class for you, I did things like this using a single part. So the first part of this presentation, this video, is going to be modeling this thing with a single part, okay? And then after I do that, I will come and do it as an assembly. An assembly being a part that is this box here, think about it, or half of it, whatever. A part that is this plate here, or half of it, and a part that is this rod, obviously not the other one, we're just doing half of it. Okay. So either way, whether you do it as a single part or you do it as an assembly, you have a choice. Making the whole thing and then start splitting it so that eventually you end up with half of it. Or if it's easier for you, just start modeling half of this, okay? And that's exactly what I'm going to do. All right. So first thing I'm going to do is to create this this box here. So let's go there. Start with a part file. Remember, single part file. So we go there. We say part. Say OK. By the way, if you give this thing the name that you want right now, as soon as you click on the floppy and you put it in the right folder, it uses that name. So for example, what I mean is this: 1, 2, 3, 4, 5, 6, 7, 8, 9. Your last name is Saiwu, T-S-A-I. Wu. Somebody, two people which are well known in the area of composites. Stefan Saar is a prof at Stanford University, and we'll call it as a single part. Single, just so that you remember what this thing was. And I mean, if there's a problem 1 or problem 2, whatever, just just add to it, whatever it is. Okay, so notice that the tree will give me that name, and if I say file save management, the name is already changed here. You say save as, we use that same name, but I'm going to use desktop. I'm going to start a new folder, and this is a lab 53, and I'm going to call it a single part, okay? Single part. Okay, all right. So there is our single part in that folder with the proper name because we initially put it. If this is confusing for you, do it the way you're used to. But remember, this must be properly named. Your student ID number, your last name, and some description. Problem one, problem two, whatever. Now let's make the half of that box which is horizontal. What I mean is half of this. So that's going to be, what is this? 4-inch. Height of it is also 4-inch, but the width of it is 2. Okay, so let's go on this plane. We sketch a rectangle that is 4 by 4 by 4 by 4, and then we pad it by 2 inches. Now, let's dimension this thing. So this is 4 inches, and this is 4 inches. Exit, and we want to pad it. Notice that we can't pad because you're in generative shape design. You have to go to part design. And then pad it by 2 inches, half of that width. This whole thing is 4. We're doing half of it, just the front piece. Okay, now, let's click on the floppy. It's going to get saved. Then we're going to create the surface, the plate at the bottom of this. Now let's check the dimension here. It says the length of this is 14 inches. There's 2 ways you can do that. You can make a plate that is 10 inches long, or you can make it 14 inches long. There is a subtle difference between the two, but for these type of problems, we are not going to worry about that. So let me do it the way I want, 10 inches long, okay? Starting from here, 10 inches long, okay. And then the width of it is 2, of course. So here, on this horizontal plane, I will sketch, okay? There are different ways of doing it. One way, this is one way, okay, is to draw a line from here to there, 10 inches long. Let's make sure it starts at that location. Control that. Make it coincident. This thing being 10 inches. 10 inches. Okay. Exit. And then pad it by... oh, that's on the wrong side. This was on the wrong plane. I wanted to draw it like this, okay? So I should have used a different plane. Okay, let's go clean this up. Just to make your job easier, I'm going to delete that. Although it's not necessary, you can change the support, but I'm not going to do that. I'm going to delete this, okay? Delete. Sometimes it's easier to get rid of this and do the thing that you want faster. On this plane, this is on the YZ plane, sketch. Okay, that's better. So draw a line from here to there. Make sure that this is coincident with that. That's 10 inches. 10 inches. Say OK. And then exit. And then we pad it by 10 inches. Sorry, 2 inches. 2 inches. Now, you want to create a surface, so you can't do it here because this is part design. So you go to generative shape design, and you can sweep it by 2 inches. Moral of the story is make this any way you want. Okay. Now my rod is going to go down here. So this coordinate, the coordinate of this point, is let's see now, -6. Okay. So starting from here, go down by -6 or by 6. Okay. So let's go ahead and do this. Okay. So this is fine. Now we're going to create a line. Starting from this, actually, you know what? Starting from that corner, from here, Let's actually do a point and direction, a line and point and direction. The direction is Z, and you go by 6. Oh, wrong direction. Flip it. -6. There we are. Actually, this is not the line that I want. The line that I want is from here to here. So I could have created a point, okay? And, here I created an extra line, which I'm not going to use, okay? No problem. So I'm going to do it like this. I create a line, point to point, from here to there. Okay, this is going to be my beam. That I'm not going to use, okay? Now I can't delete it because I use the end of it, but I can always hide it and don't mesh it. Just as simple as that. Don't mesh it, okay? All right, so everything is made out of steel. Please watch the videos for sections 51 and 52. They're different type of problems and done differently, okay? So what was it? This was aluminum, I say. Default steel structure. Okay, metal, steel on the entire part. We say okay, and we are done. So you click on the floppy, everything is going to get saved. Now we're going to go to generative structure analysis. Catia immediately sees a solid object here. It gets excited and meshes it. Okay, so I can say, show me the mesh, and show it to me. Okay, but this surface, this plate, and that beam, we have to do that. Remember, there's also a line in the background which we are not going to use anyways. Okay, so let's do the surface mesh or shell mesh on this. Let me make this thing a little smaller, 0.5. Okay, I'll use linear. Very good. And give it the thickness there. Now I don't remember what the thickness of this thing was. It says thickness of 0.25 inches. Excuse me. 0.25. All right. Okay, you want to see the mesh? Right click mesh visualization. You'll see the solid mesh and shell mesh, but not the beam one. We haven't done it yet. So deactivate this. Deactivate that. Okay, now go and do the beam mesh. There's the beam mesher. Select the thing that you want to mesh right there. Now notice that because I drew a line in space, I did not have to join it. But if this was a sketch, in space, then you would have to join it, otherwise you can't measure. Okay. Okay, 0.25. That'll probably put about 10-15 elements through the length. Okay, and the thickness, the cross section is a circle. So let's select it. Here's the support. It's a circular beam. Radius. Let's see what the radius is here. The radius is a circular cross-section of diameter 0.25, so radius 0.125. So 0.125. 0.125. You say okay, and there you are. You can see that. You see? And this is to scale. I mean, this is a to scale. Okay, now if you see, show me the mesh, it'll show you all 3 types. This is why we call it hybrid. These are the beam elements. Beam element here. Look, this is element number, zoom in. Element number 9548, going between nodes 2403 and 2402. I just wanted to show you that there are elements there. Okay, deactivate the mesh for the rest of the problem. Deactivate. Okay, now, this point is clamped. So, there's the clamp. Okay. Make sure you don't put it on a point. There is no point here because I don't have a point. I didn't create a point there. There's a vertex there. Now, let's see now. This whole thing, well, let's do the symmetries. Okay. That face is a surface slider. Surface slider is a fancy way of saying there is no displacement in the direction X, like that. Okay. And this edge, this is a symmetry edge for the shell. So let's do that. User-defined restraint, I put here in the plane YZ, ZY symmetry. You can see that it sits in the ZY plane. ZY plane means does not move in X, and rotations are exactly the opposite. So this edge does not move in X, rotations are exactly opposite. Now, I'm going to run this thing to show you that this is going to bomb out, and we'll see why. Okay. Let's give it the load. Okay, so the load is acceleration for this and that surface in the direction. What is that? Direction Z, not X. Direction Z, negative 9.8. It says 9.8 meter per second square. So internally, it's going to convert it to acceleration, which is around 380, I think, inch per second square. But you can reset your units if you want, but that's fine. They'll do the job. Okay. Now let's save our analysis file. File, save management. There is the analysis. Save as. Okay, so what did we call this thing? We call this thing student ID number 123456789 dash SAIWU TSAIWU and single part. Okay, single part. Okay. Now we're going to run this, and we're gonna see that it will bomb out. So let's try it. It bomb out because this block has no idea that it's attached to something else. This rod has no idea, or this beam has no idea it's attached to something else. And in fact, if you plot the deformation, you can see that it kind of wanders around. These things are, not connected to each other. So we have to create connections. Okay, now connections not only apply to the assemblies, but they also apply to parts. Remember, we created a problem where we had a folded sheet metal with different thicknesses. One way of doing it, the one that I did not advocate too much, was creating a connection and making that connection fasten. Okay, so let's deactivate this. I showed you other ways of doing it. Okay, good. Now, first of all, let's create a connection between the corner of this line, or the vertex of this line, and the corner of this plate. So, analysis connection. Let me hide this surface so that you can easily see this point. There we are. And for the second component, I need to select the vertex of this plate. There is no point here, so I can easily select it from here and right-click so that it goes back there. So we created one connection, and let me give that thing a meaningful name. So I will call this, I'll call it beam, connection between beam and plate. Okay, good. It's in the tree right there. Now, we also want to create a connection between this face and that face. Okay, okay. Or you can select the whole body here and that face, that plate. So let's create another one, connection between the block and the plate. And the plate. For the first component, I select this. Okay, no, not that one, not that face. Cancel. Now, I can select this face, or I can go and select the pad. Even if you selected the pad, it will select that point. Just to convince you, let me uncheck that. See that? If you go and select the pad, where is this? Pad right here. See, it just selects the face. Okay. All right. So I leave it to you to decide which one you want to do. Okay. It may be easier actually, although I didn't do it like that in the lab sections 51 and 52, it may be easier to say, okay, that face, okay, and for the second component is this face. There may be some issues here, and we will see what's going to happen. Okay, say okay. This one was, yeah, this connection, yeah, okay. So let's go ahead and do the connections, the type of connection. This was just defining them. Now, between the vertex and this vertex, it has to be rigid. So you go to distance analysis connections, you select this rigid connection, and you select it from the tree right here. See, beam, plate, it's rigid connection. Now, this other one, we're going to call it fasten. So whereas fasten is not distance connection property, it's a face-to-face connection property right there. This is a fasten, the third one. So we select it from the tree. Notice that it puts this fastener sign here. And we'll see if this runs into a problem, we'll do it a different way. Okay, so let's save everything and run it. Okay. It looks like it ran. There was no problem. Okay. So deflection. Change the scale. There we are. Isn't that the way it's supposed to do it? Sagging under its own weight. See that? Sagging under its own weight. Okay, good. Do you want to look at the magnitude of deflection? No problem. There's the size, 1.57 inches. That's probably a lot of deflection. I don't think the stress is going to be, well, we have no confidence in these things. You cannot believe these unless you do a mesh conversion study. Okay, as simple as that. Doesn't matter how you slice it. You cannot believe these without mesh conversion study. Okay, so on the surface, it looks like the place where we have the biggest problem is over here, but there can be. This is on the surface. If you want to look at for example, stress distribution in this area, you have to make a box and just stay away from that. And just to show you that, let me try. As far as this problem is concerned, we're done. We're going to come back and do it as an assembly. But I want to show you something here. Right click, deactivate it. Let's create a group here. I don't know, a box group maybe. Okay, very good. Stay away. And the box is already staying away from these points. So resize the box. So there we are. Okay, and then say, okay, show me the 1 meter stress. Right click, activate, but don't show me everything. So double click, just show me the box. Where's the box? Right here. And find and don't show me the group. You see, before there was a gigantic stress here, which could have been artificial, completely artificial, and you could not. It masked everything there. Okay, it masked everything there, and there was a 20,000. But if you look at the stress distribution in this area, okay, it's going to be almost 3,000, which is not that bad. Okay, of course this big block is going to move as a rigid body. There's very little stress in it, basically. With the heavy object, you just make this thing bend. Okay. Now, what I'm saying is that when you see red, doesn't mean that is the critical area, because remember, you're welding a beam to a plate and you're making the plate bend. Of course, there's going to be gigantic. There's no way you do something like that, because you know for sure that's going to cause a problem. This is going to be weak point. But okay, good.